Discrete tomography asks a highly difficult mathematical question. How do you perfectly rebuild a complex internal structure when your only data are flat, lower-dimensional slices? In applied fields like medical imaging and cryptography, researchers frequently find themselves with only a handful of one-dimensional projections. From those sparse lines of data, they have to mathematically deduce the exact two-dimensional or three-dimensional source object. But the process contains an inherent flaw known as tomographic ambiguity. Because a projection inherently flattens data, entirely different internal structures can cast the exact same sequence of shadows. Without adding further constraints to the system, achieving a perfect, unique reconstruction is mathematically impossible. Reconstructing a true matrix from its projections is an exercise in managing this ambiguity. To isolate the correct source, mathematicians must find structural rules that eliminate false duplicates. To understand how these rules work, we examine a specific puzzle space, alternating sign matrices, or ASMs. This diagram shows a standard alternating sign matrix. It is a square grid populated entirely by zeros, ones, and negative ones. Adding the values in any single row or column sums exactly to 1. Furthermore, the positive and negative ones strictly alternate in sign. We analyze this matrix with an X-ray, generated by summing its antidiagonals. Sweeping downward, the sums deposit into a vector below, 0, 1, 1, 1, 0. But tomographic ambiguity remains. A completely different matrix yields the exact same vector, preventing unique reconstruction. While some X-rays produce duplicates, a highly specific subset of alternating sign matrices are so rigid they point back to only one possible grid. The mathematical objective is to isolate the specific architecture that locks an alternating sign matrix into a single, unfakeable X-ray. The set of alternating sign matrices uniquely determined by their X-rays is in perfect one-to-one correspondence with the Catalan family of numbers. We can model this relationship visually using what are known as Dyck paths. A Dyck path is a geometric staircase walk. It moves from a starting point to an ending point using only rightward and downward steps, while adhering to one strict rule. The path can never cross below a primary diagonal boundary. Mathematician Martin Ruby introduced a method, known as Map-A, to translate a one-dimensional Dyck path into a two-dimensional alternating sign matrix. This diagram shows an empty grid of size n by n. We draw a Dyck path on it, starting at the top left and moving to the bottom right, tracing east and south steps while staying strictly on or above the main diagonal. The first step in building the matrix is reflecting the path across the main diagonal. This creates a mirrored boundary line in the lower half of the grid. Next, we populate the numbers. We identify the peaks, the outer corners of the upper path. We then take positive ones and fill the vertical space lying directly between each peak and its mirrored counterpart on the lower path. We apply the opposite rule to the valleys. We locate the inner corners of the upper path, and negative ones drop into the cells between those upper valleys and the lower mirrored valleys. Finally, every remaining empty cell in the grid fades to 0. By mapping a Dyck path through these specific peak and valley mirroring rules, we guarantee the creation of a diagonally symmetric matrix. The rules force the Catalan family's geometry directly into the grid. We now have to test if this resulting matrix is genuinely unique to its X-ray. A known mathematical property is that transposing a matrix preserves its X-ray. Because of this, only diagonally symmetric alternating sign matrices have any potential to be reconstructible. To test the integrity of that symmetry, Ruby designed a second mechanism, Map-M. This animation demonstrates Map-M's core metaphor. Imagine a light source shining from the top right or northeast of the generated matrix. The positive ones in the grid act as solid objects, blocking the rays of light. Those positive ones cast a shadow toward the southwest. If you trace the exact boundary line separating the light from the darkened shade, the contour forms a perfect Dyck path. The formal proof, Lemma 3.2, applies an operation based on this boundary. The map takes the matrix entries lying just outside the shadow and reflects them across the subdiagonal. Map-M acts as an identity map, leaving the matrix completely unchanged, only if the structure was built using the Map-A generator. If the input is any other valid matrix, the shadow reflection logic inevitably breaks its symmetry. This proves the Catalan-derived structure is highly rigid. The shadow map demonstrates that any deviation from the Dyck path generator shatters the exact symmetry required for tomographic uniqueness. With the structural rules established, we can examine lemma 4.1. This is the final geometric proof showing why an X-ray cannot map to two different matrices if they possess this specific Catalan structure. Assume we are sweeping through the matrix diagonally from the northwest. We have successfully rebuilt the first k antidiagonals from their sums, stopping at an unknown boundary line where we need to deduce the next row of data. The reconstruction is constrained by the absolute rules of the alternating sign matrix. Every row and column must begin with a +1, and all subsequent non-zero entries must alternate in sign. Moving to the next unknown antidiagonal, the alternating rule creates literal dead zones, specific cells along the diagonal line where numbers mathematically cannot be placed. The logic here is strictly positional. If you place a +1 in these forbidden spaces below the main diagonal, the sequence dictates another +1 must be directly above it. The rules forbid two +1s in a sequence without a -1 between them. With those cells eliminated, we are left with the only valid geometric spaces, a small triangular region bounded by the previous data. Because no other cells on the antidiagonal can hold a value, the required sum from the X-ray must be satisfied entirely within this tight boundary. To hit the correct sum, the available triangular region must be filled completely with either ones or -1s. There are no other variables to adjust. The strict alternating rules of the matrix intersect directly with the rigid geometric boundaries of the Dyck path. This eliminates all combinatorial freedom, forcing the data to resolve into exactly one configuration. By mirroring the peaks and valleys of a Dyck path, the internal variables of an alternating sign matrix are completely locked. The geometry strips away the tomographic ambiguity. As a result, the specific subset of alternating sign matrices, uniquely determined by their X-rays, maps directly, without exception, to the Catalan numbers. The actual publication of this paper is notable because Ruby did not start out trying to prove a link between discrete tomography and Catalan numbers. The coincidence was discovered empirically. During the research phase, the raw statistical counts of these unique matrices were submitted to the online combinatorial database, FindStat. The database automatically recognized the sequence. By matching the generating functions, the software algorithmically linked the tomographic X-ray problem to the classic Catalan family through pure data correlation. This finding demonstrates how large-scale databases can identify patterns that might otherwise stay buried in raw matrix data. Data matching through FindStat provides mathematicians with empirical evidence of structural bridges between families. By identifying these connections first, researchers can then focus on building the rigorous proofs required to formalize them.